back to Laplace Transform. This first page is a little summary of the properties we have proven. We've proven all of these four properties. Linearity for Laplace Transform. Laplace Transform of any function f that is continuous and of exponential order times e to the at is exactly Laplace Transform of f, but you have to plug in, for the place of s, you would plug in s minus a. This property relates f prime to f, which is going to be very helpful to us. So Laplace Transform of f prime is negative f of 0 plus s Laplace Transform of f. It's not a surprise that f of 0 shows up. It's almost like an initial condition. If you have f and f prime as a differential equation, you would need f of 0, wouldn't you? So it's not surprising. In fact, it'll be clearer once we prove the kind of the extended version of this property today, okay? And then Laplace transform of a power of t times f is related to Laplace transform of f by taking the derivative with respect to s n times, because n here, you have the exponent is n. So if it's t squared, you differentiate twice with respect to s, and you hit it with Laplace transform of f. So these are the four properties we proved last time. We're going to start setting up or creating a table of things we have proven or have been done for homework. So you can always use Laplace transform of 0 to be 0 or Laplace transform of 1 to be 1 over s, so long s is positive. So once we have a table, feel free to use these anytime you want. Last time we proved these three, and I think I gave you these for homework. So today we're going to go over them quickly. I've never gone over homework, but I'm doing it here because I'm going to show you a different approach on how to address especially these two, okay? I mentioned to you last time that you should, the natural thing to do for Laplace transform of cosine beta t is just the integral from 0 to infinity e to the negative st, and then the function cosine of beta t dt. And I said you could use integration by part. The cosine gives you negative sign, and the negative sign gives you cosine. That means you would have to integrate twice, integration by part twice, and eventually you will get this answer that I put in here. And while you're doing the first integration by parts, the sign of beta t will show up, and from there you can borrow Laplace transform of sine of beta t. So what I'm going to do today, I'm going to show you how to do this in a different way. I hope you did it using this. It's important to go through this at least once to see that it works and to practice your techniques of integration and just to feel comfortable with this, okay? So that's a little summary with the properties and some of the things we have proven. Anything that is proven, feel free to use anytime you want. So what I'm going to do next, we're going to go over this one. And again, you probably did the integral from 0 to infinity e to the negative st, t to the n, and did some work and eventually got this. But I think we could just use this very quickly, because if you notice here, if I force the function f of t to be 1, which is definitely of exponential order, because we know that 1 is between negative e to the at and e to the at, and we know that 1 is continuous. So therefore the integral exists, the integral converges. And by the way, let me just say this quickly. Laplace transform, we said, of f by definition, we said it's this, right? what's going to force this integral to exist? This is an area under the curve. And for the area under the curve to exist, this piece here that we added, that came from nowhere, if you think about it, this function is a function that looks like this, assuming s is positive, right? So as s goes to infinity, this piece here damps this function completely. No matter how it looks, no matter how f looks, e to the negative st is when it's going to force it to be asymptotic to the x-axis when x goes to infinity. And that's why last time when we integrated a couple of times and we got to something like this, that's very first piece, whatever it was here, that's very first piece always gave me 0 if you think about it. Okay, so go back to the previous presentation. We always had something to infinity, so to speak. We got 0 minus, generally we got something like 1. So, and that's not a surprise because, in fact, all of them will give you 0. So that's really the main reason why this little factor was introduced. Okay, so let's go over this one quickly. You could just use this by forcing f of t to be 1. So I'm going to force f to be 1, and I'm going to use the definition. Hey, this is the definition, right? This is the definition. Laplace transform of 1 is just 1 over s because it was proven. And now we need to differentiate 1 over s n times with respect to s. I didn't write anything, but I'm sure you could follow me here. So the function is 1 over s, right? If you differentiate it once, you get negative 1 over s squared. If you differentiate it the second time, you get negative, which is 1 times 2 over s fourth. I should say 2s over s to the fourth. By the way, I don't know if you know this, but if you have a quotient rule where the top is 1 or even a constant, okay? You don't need to use the quotient rule. It's always negative cf prime over f squared, okay? The reason is because c prime, quotient rule says c prime f minus cf prime over f squared. Well, c is a constant, so c prime is 0. So that kills this piece. So when I see this, I immediately think of negative f prime over f squared. Well, the derivative of s is 1, so you get negative 1 over s squared. Here it is. And then you do derivative, ignore the minus, okay? Ignore the minus. Let's just leave it to the side. Derivative of s squared, which is 2s, over s squared squared, which is s to the fourth. But we had a minus. So minus and minus gives me a plus, and s to the fourth gives me s cubed. So this one is just 1 times 2 over s cubed. If you do it again, you get 1 times 2 times 3 with a negative sign, and the derivative of s cubed is 3s squared over s to the sixth. Once again, s squared cancel, you get s to the fourth at the bottom, and you get 1 times 2 times 3, which is 3 factorial. So very quickly you could see that if you differentiate this n times, you're going to get plus or minus, plus or minus, plus or minus. That's this piece. That went here. And the plus or minus gave me here. And at the top you get 1, you get negative, you get 1, you get negative 1, you get 2, you get 6, right? This is 0 factorial, this is 1 factorial, 2 factorial. And notice that if I differentiate once, let's call it f prime, I get s squared. So the exponent of s is 1 more than the number of times you differentiate. If I differentiate the second time, f squared, I get negative 6 over s to the cubed, right? This number is 1 more than the number of times you differentiate. And hence, if you differentiate n times, the exponents of s will give you n plus 1. Okay? I'm sure you can get this one. Now, negative 1 to the n times negative 1 to the n, oops, I'll go back to it. Okay. Negative 1 to the n times negative 1 to the n, they have the same exponents, so it's just negative 1, the whole thing to the n. Okay? It's just this. It's negative 1 times negative 1, the whole thing to the n. Isn't that true? And negative 1 times negative 1 is 1. And 1 to the n is 1. Is that always true? Is 1 to the n always 1? The answer is yes, so long n is finite. Okay? So if n is infinite, 1 to the n is not 1. It's not 1, okay? 1 to the n is an undefined expression. So if I say to you, what's the limit as n goes to infinity of 1 to the n, this is undefined. Okay, so be careful. But we're assuming here n is finite, right? Because you differentiate in n times, so clearly n is finite, and therefore negative 1 times negative 1 is 1, and 1 to the n is actually 1, and hence my solution. Okay, so now you can add this to your table. You can use it anytime you want. So this is like your toolbox, okay? You think of yourself as a plumber, and you have tools in your toolbox, and you go to people's home to fix something. Feel free to use these anytime you want, so long you have proven them, and I think we have proven all of these four. Of course, s has to be more than 0 here, s more than a, s greater than 0. So let's go back to now. I think I'm done with that question. Oh yeah, so what I decided to do is pick the problem from the homework and try to take advantage of this to get this one. And I know most of you got it, but let's go through it quickly. Laplace transform of this quadratic is the sum of Laplace transform because of property number 1. Okay, proven. And Laplace transform of a constant times a variable, you can pull the constants out. That's part of the linearity. The negative 3 comes out, and there is nothing here that comes out. Laplace transform of 1 is 1 over s. Laplace transform of t squared, you just replace n by 2. So you get 2 factorial, which is 2, over s to the power of 2 plus 1, which is s cubed. Here it is. And the 5 goes there. Laplace transform of t. See, this is powerful. It gives you all sorts of powers, right? You can use it anytime you want. We did exponentials, and we did powers. And of course, cosine and sine. And aren't these the 3 functions we have used? You know, the typical functions for guessing solutions to the homogeneous equation. Exponentials, powers, and sine, cosine. Okay, so that's why we think of them, and these are just constant, they're useful. Okay, so Laplace transform of t, you replace n by 1, you get 1 factorial, which is 1, s over 1 plus 1 is, s to the power of 1 plus 1 is s squared, and this is the answer. Okay, hopefully this is what you got for the solution of the problems from the homework. So now let's go to the cosine and sine. And I love to leverage my time. This method that I'm going to show you, not only that it is much faster than the one you did on the homework by trying to integrate using integration by parts twice. You buy one, you get the other one for free. That's the beauty. So Euler's formula says cosine of an angle plus I sine of an angle is e to the angle t, right? I put the parentheses in the wrong place, but it's okay. So we know Laplace transform of exponential from the first one here. Laplace transform of e to the at is 1 over s minus the coefficients of t. So Laplace transform, I want to use Laplace transform of e to the IBT, right? And we know how to do it. Let me write it down. I forgot something, but I'll do it here. So Laplace transform of e to the IBT has to be 1 over s minus the coefficients of t. So what I forgot to do here is what? I forgot to apply Laplace transform. Okay? So Laplace transform of this equals Laplace transform of that. Sorry. Okay? And Laplace transform of each. Now Laplace transform of this, I just said it's 1 over s minus ib. Well, if I multiply by the conjugates, multiply by s plus ib, I get s plus ib over s squared plus b squared. Or s squared minus I squared b squared, and I squared is negative 1, right? A minus b times a plus b is a squared minus b squared, so you get this. So that means Laplace transform, I really messed up this page. Laplace transform of this is the sum of Laplace transforms. So it is Laplace transform of cosine bt plus Laplace transform of sine bt, and I'm going to pull the I out. Remember, this works for any a and b, even if a and b are complex numbers. Okay, they don't have to be real numbers. So Laplace transform of cosine bt plus I Laplace transform of sine bt is this. And I split it right there. So I took the real parts and I took the imaginary parts separately. And therefore, Laplace transform of cosine bt, the real parts basically goes with the real parts. So you get this. And Laplace transform of sine bt has to be that. Isn't that beautiful? You get both for free. Or actually, you get one for free. So now, we have proven this one and that one. You get them at the same time. So that's the nice thing about this problem. Okay? So the moral of the story here is you really want to take advantage of properties. If you don't take advantage of properties, you're going to integrate left and right, and some of the integrals are ugly. Okay? So what I'm going to do now, I'm going to go back to this one. And we are going to generalize. So what it says is Laplace transform of f prime is a function of Laplace transform of f. The initial condition is there and s pops up. What happens if I do Laplace transform of f double prime or triple prime? Because linear ODEs, sometimes you have an ODE of second order or third order or fourth or nth. But this is only relating first order. This is a first order linear equal. If I have an ODE of first order, I can use this. But if it is of second order, I need something better than this, okay? So that's what I'm going to do next. All right. So here is the property number 3. Okay? So now what we want to do is find Laplace transform of f double prime. So I'm going to write f double prime as f prime prime. So think of this as a function, let's call it f. And we know how to handle Laplace transform of something prime. Something prime. So that has to be negative f, capital F of z, of 0, plus s Laplace transform of capital F. But we know f prime. We know f prime is just f. So I am not trying to differentiate this and differentiate that. That's not what I'm trying to do. What I'm trying to do is replace f prime, the one in red, you can call it capital F. Laplace transform of capital F prime is this. It's negative capital F of 0 plus s Laplace transform of capital F. But we know capital F is little f prime. That's all I'm trying to do, okay? Now, so then what do we get? Well, we get negative f prime of 0, here it is, plus s, here it is, Laplace transform of f prime, which was found earlier. So we replace this by this, put it here. Distribute and bring the s squared. I like to start with s squared. So you get s squared Laplace transform of f minus f or s, f of 0, minus f prime of 0. Notice again that if you want to relate f double prime to f, you need two initial conditions, f of 0 and f prime of 0. And they showed up, which is really cool. I did the same thing for a triple prime, okay? Just quick notation first, so you understand. When you pass 3, it gets really ugly, right? You do like 4. So one way to say that is just to put 3 in parentheses. It just means you are differentiating f with respect, you're differentiating f 3 times. So this would mean f parentheses 4, okay? So that's the first thing I want to say. The second thing is I'm going to call f triple prime f prime double prime. And feel free to call f prime capital F. So basically, f triple prime is capital F double prime. And I'm going to use the same trick. So it's s squared, look here. So f triple prime, I'm going to see it or think of it as something double prime. Capital F double prime. So Laplace transform of capital F double prime is s squared, just look here, is s squared Laplace of f prime, not f, but f prime now, minus s f prime of 0 minus f double prime of 0. Every time I see a prime, I call it double prime. Every time I see a little f, I call it f prime. And every time I see a little f, I call it f prime. Why? Because every time I see f double prime, I call it f triple prime. And I'm just using the same trick, okay? Go through it very slowly and it'll make perfect sense to you. So now what I did, we know what this is. It's here. So I replace it. That stays, that stays, that stays. Distributes, you get s cubed Laplace transform of f minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. See? So Laplace transform of f triple prime, you get a Laplace transform of f times some s cubed and s squared and s and nothing. For the double prime, you get the s squared and the s and nothing. For the prime, you just get the s and nothing. Okay, so you could probably see what's coming up here. Laplace transform of f differentiated n times. That 3 matches that 3. That 2 matches that. What is it? 2. Okay? That 1 matches that 1. So we're going to get s to the power of n, Laplace transform of f. And then the powers of s drop. So s to the n, s to the n minus 1, s to the n minus 2, all the way to s, and then no s, 0s, no s's. Okay? And then in here, if you notice, In here I have f of 0. In here I have f of 0 and f prime of 0. In here I have f of 0 and f prime of 0 and f double prime of 0. And of course you can tell what's coming up here. You get f of 0, f prime of 0, f double prime of 0, f to the n minus 2 primes of 0, all the way to f of, think about it, just change n into 3, okay? If you plug in 3 here, you get s cubed, Laplace transform of f, here it is. S squared, because n is 3. F of 0, here it is. N is 3, you get 1 minus s, f prime of 0, here it is. The last one is 3 minus 1, which is 2. So f double prime of 0, here it is. Okay? And of course there is nothing in between, there are only 4 terms. Now, I jumped, this is not a proof, okay? Let's just be very clear. I would call it a proof, not a proof. So if you really want to prove this, I don't know if you've seen the principle of mathematical induction. If you haven't, I suggest you look at it. It's not hard. It's a 3-step process to prove equations that involve integers. Actually, positive integers, including 0. So anytime you have, so if you think about this, if I ask you to prove this, because this is not a proof, I just went from, we proved this, then we actually proved that, and then we proved that, then I jumped to the nth derivative. That's not a proof. I didn't prove anything, okay? Notice n takes integer values, positive integer values, right? Including 0. We can definitely prove it. If we have some time this trimester, I may want to prove it to you. It's not hard at all, but you must know the principle of mathematical induction. In fact, I'm going to give you a small homework problem where I would like you to use the principle of mathematical induction to prove this. In any case, this is not a proof, okay? I just gave it to you. We would have to prove it using this principle. Okay. That is beautiful. This is powerful, okay? So this is the general case of this one, okay? All right. So here's your homework. I would like you to do these 3. Please don't integrate, okay? Use the tricks we just did. Use this table anytime you want, okay? And you're going to get these in about a few seconds. Each one of them should take you about 15 seconds, okay? Then from the book, I would like you to do problems 1 through 7, 1 through 4, and 6 and 7. 1 through 4 and 6 are really quick, just like these. Number 5, they ask you to verify this. Now you might say, well, we proved it anyway. In fact, we proved it today. Why should we prove it again? I would like you to use the principle of mathematical induction to prove number 5. And then number 7 is extremely fast, but we haven't talked about the inverse Laplace transform yet. Basically what it says is, for example, Laplace transform of 1 is 1 over s. Isn't that true? So basically, if 1 is in the domain and 1 over s is in the range, Laplace transform is the function or the operator that moves 1 into 1 over s, or moves 0 into 0, right? Or moves e to the at into 1 over s minus a. Well, if I have this, can I use the inverse Laplace to guess that? So basically, the inverse Laplace transform of 1 over s, because 1 over s is so famous in the range, you would know that has to be 1, okay? So we haven't done any of that stuff, but I still gave you one quick problem. I think it's number 7. It's very quick because it's going to be one of those recognizable outputs, okay? The inverse of Laplace transform of 1 over s has to be 1, right? And if it doesn't look exactly like it, you just have to do a little algebra to make it look obvious, and then you go back. That's all it means. So, in summary, this one, and this one, and 6 out of 7 are extremely short. So that leaves you with number 5, which is, I would like you to verify this. Please, I don't want you to use this method. Okay, I already did it. I would like you to use the principle of mathematical induction to prove that Laplace transform of t to the n is n factorial over s to the n plus 1, assuming s is positive. Okay, so I hope this was helpful. And next time we're going to work with inverse of Laplace transform. Of course, there is a condition on when to use the inverse. We'll talk about that. But for now, I think this suffices. Take care.